Okay, so we're looking at piecewise functions, and what we went over in class was taking a look at exactly what a piecewise function was. Now, the form of the function is actually given in two or more equations. So we're going to use this equation and what that looks like from 0 and below. So everything on the left side of the graph is going to possess what 3x plus 5 looks like. And everything past and equaling 0 will look like 4x plus 7. But the first thing we do is we're just going to figure out how to evaluate things. So the first problem is evaluate f of negative 2. So what I say here is since negative 2 is less than 0, remember, this is an x value. It's saying evaluate the function when x is negative 2. Well, if x is negative 2, well, which one of these functions does that fit? You need to choose the first one because the negative 2 for an x value is less than 0. So if that's true, that's the one we choose. So we're going to choose 3x plus 5. And when we do that, we say f of x equals, well, 3x plus 5 because that's the one where x is less than 0, when x is less than 0. Right now it is because it's negative 2. And you can go through the work here, and you've seen function notation before, but all we're doing is replacing the x value, and we're going to see what the y value is. When you calculate all that through, negative 1. So basically what that's saying is x is negative 2, y is negative 1. That's a point or a coordinate that's on the line of 3x plus 5. But that's all about what do we choose? Do we choose the first equation or the second equation? When you evaluate functions like this, you need to be able to choose. So let's look at one where we choose the other one. And y, remember, x is the input that goes in function notation, so it's 0. Well, is x less than 0? 0 is not less than 0, so we see that that's false. So we can't choose the first equation. But it is true, 0 is greater than or equal to 0, which is the second one. So now we're going to choose the second equation, which is 4x plus 7. And we do the same thing we did in the previous problem. Input x is 0 into the problem, and we come out with 0, 7. And that is a point that is on that line. And we know that because this is actually the y-intercept. And we know that that is the y-intercept. Here's the second problem from the book, number 38. This time it's defined as two different linear equations and still giving us the same if x is less than 0, if x is greater than or equal to 0 as the two parts or the two pieces of the function. The first one I'm asking you to do on the left is f of negative 3. Since negative 3 is less than 0, we choose the first equation. And we just input that value into the function, as you can see with the work shown. All we're doing is we're inputting negative 3 into notation and also into the equation to figure out the coordinate. So this coordinate is somewhere on that line at negative 3, negative 19. So it's one of the many, many points on that line. I choose the second problem. I say, well, evaluate f of 0. This time, again, you'll notice that 0 equals 0, so we have to choose the second function. We plug it in, substitute, and we see 0, 3. And again, we can see that's a y-intercept. So evaluating functions is all about, on these piecewise, is all about choosing the right one depending on what x is, depending on what the input is in the function notation. Okay, so in this problem, what I'm doing is we're still looking at piecewise functions, but what we're doing is we're going to see what they actually look like. What does it mean on a graph? So as you can see, the first equation is 1/2 x squared, and we know that that's a quadratic because x is raised to the second power, so it's going to have that parabola look to it. Now you can see on the graph that it stops right here at 1. It stops because it says x is less than 1. So it cannot equal 1. That's also why you see that open circle at 1. X is 1. And that's where that stops. So everywhere from below 1, we would be looking at this quadratic, this 1/2 x squared as the function. Once we run past 1, or exactly at 1, see that is filled in so it can equal that. If we were looking to evaluate the number 1, we'd have to use the second equation, 2x minus 1, because that's what it's telling us up here in the notation of the piecewise function. It's saying when x is greater than or equal to 1, use 2x minus 1. On the right, I give you some examples of how to write this range. You're going to be asked to graph and then state what the range is of these piecewise functions. So range, remember, is y values. As you can see on the graph, we don't go below the x-axis. So the x-axis is a y value of 0. Now, it goes right through it, so it can equal it. That's why we use the square bracket 0. That's the lowest point of both of these two functions that we can get to on this piecewise. This is going to go on forever, and so is this. Up and to the left, up and to the right. But since we're only looking at directions up and down, if it's going up forever, well, that's going to be infinity. Set builder notation I've also given you above it. Interval notation is a little easier, but set builder notation is important as well. But notice we have the less than or equal to, which also means square bracket in interval notation. The less than sign for infinity is going to give us this parenthesis. When you evaluate from a graph f of negative 2, well, when x is, this remember is x is negative 2, so the x value is negative 2, that's got to be below 1. Okay, so that means we choose 1/2 x squared, and that's what you see the work for here. In blue, I give you an example of one where you get to choose the other one because x, which is 2, is greater than 1. So you have to choose the second one.